Hi everyone, I am Joany Mariño and I am going to be talking about how resource and seasonality drive interspecific variability in a dynamic energy budget model. Animals show a vast array of phenotypic traits in time and space. These variation patterns have traditionally been described as ecogeographical rules. For example, the tendency of size to increase with latitude within species or in groups of closely related species is known as Bergmann's rule, while the tendency of increasing clutch size with latitude is termed Lagg's rule. Despite considerable evidence supporting both patterns, the processes explaining such variation in traits within species and among related species remains controversial. Recent hypotheses have explained the variation in body size and reproductive output based on food availability. In the resource rule, Bergmann and Lagg's patterns are determined by the size, abundance, and availability of food. Similarly, the ENPP rule states that the mechanism driving food availability is the global distribution of net primary productivity during the growing season. For both hypotheses, it is the seasonal cycle of food surplus and food deficit that explains geographical rules. For example, when we compare tropical with temperate environments, the largest animals and with greater reproductive output will occur in temperate areas because they have a greater food surplus. In this way, the variation in food availability is the main determinant of energy input. Here, I test whether resource availability alone can explain individual trait flexibility. To investigate the origin of interspecific variation without confounding effects, I adopted a modeling approach using the description of the individual metabolism proposed by the standard dynamic energy budget model. A main assumption of the model is that the biomass of an individual is partitioned into reserve energy and structural volume, or soma. After individuals are born, energy assimilated from food is first allocated into the reserve and then mobilized either to fuel somatic growth or for maturation or reproduction. For simplicity, I assume here that individuals release the reproduction energy continuously as gametes, regardless of the environmental conditions, so we neglect its potential contribution to the individual's biomass. In this model, the parameters represent the physiological processes that, together with the environmental conditions, result in different phenotypic traits, for instance, size or biomass. The combination of parameter values in the DEB model are species-specific, in a way that the differences between two species are primarily explained by differences in their parameter values. Here, I focus on the trait differences that can arise due to variation in the parameters of energy assimilation, mobilization, and allocation to soma. Despite the diversity of life history traits and strategies in the animal kingdom, not all strategies are possible. So I used my pet collection in order to select a biologically consistent parameter set that reproduces the natural variation observed across the species. So starting from all the species in the collection, which in March 2020 had a total of 2,032 species, I began my subset by selecting the species model with the standard DEB model and then narrowed down the parameter space according to the lifespan and completeness of the data. After removing outliers, I was left with 216 species, from which I looked at their parameter combinations. I discretized the parameter distribution and removed low-frequency combinations, leaving 214 common parameter combinations. Then I removed repetitions and outlier values. So finally, I was left with a parameter space that consisted of 13 parameter combinations for mobilization and assimilation. I added 3 more combinations that were in the neighborhood of my subset and used this parameter space to simulate interspecific variability. To simulate the resource or food, I assume that the food density operates directly on the scale functional response, which facilitates contrasting the model's behavior across different fluctuating regimes. In this way, I investigated the effect of a constant and a seasonal resource. For the constant resource, I modeled 5 scenarios, ranging from scarce to maximum resource availability of food, in order to provide a complete description of the effect of food availability. For the seasonal environment, I assumed a periodically fluctuating resource, using 3 average values within the range of the constant resource. Moreover, I assessed the initial resource effect, which can be understood as individuals being born at different times throughout the year. So, for example, I compared whether there was a difference among individuals born during the period of highest food availability or the period of lower food availability. To summarize, I simulated 16 species as given by the parameter combinations in assimilation and mobilization. I evaluated each of them at 3 intermediate levels of allocation to soma and 5 constant environments, ranging from scarce to complete abundance of resource. I also compared 12 seasonal environments, including 4 different initial conditions. This is a total of 816 simulations, which I conducted in R, each one with a simulation time of 3 years. Then I quantified the differences in individual traits, focusing on biomass and reproduction. To compare all the results together, I plotted here the mean value of the trait, in this case biomass, across the different food levels, from scarce to abundant. Here, each line color corresponds to the value of assimilation, while the columns correspond to the mobilization parameter, and the rows correspond to the allocation to soma. In this way, each line within a box represents a species growing under different resource conditions, and different colors represent different species. Overall, we can see that the maximum biomass increases with average food level. Now, this plot corresponds to a constant resource environment, but the pattern also holds for a seasonal resource. When we look at the cumulative reproductive output, we can see that the results are similar, with the resource driving intraspecific and interspecific differences. Interestingly, higher values of allocation to soma result in greater reproduction, which is likely caused by the intermediate values of the parameter that I evaluated, and this may not be the case when these values are closer to 1. Again, this plot is for a constant resource, but the pattern is the same in a seasonal environment. But the more relevant findings are when we contrast the effects of a constant and seasonal environments at the same average resource level. Here, I plot the resource for a mean resource that equals 0.4. Here, the points represent the average value of the biomass, while the bars correspond to the minimum and maximum value. First, we have a constant environment, where there are no bars because the biomass is at equilibrium and there are no oscillations. Then we have the 4 seasonal environments that I considered, with individuals being born at a decreasing food availability, at an increasing food availability, at maximum food availability, and at the minimum. As we can see, the individuals living under a seasonal resource can reach a greater average biomass than in a constant environment. And this is true regardless of the season in which the individuals are born. The same result holds for a cumulative reproductive output. However, here the mean reproductive output depends on the initial resource density. So, for example, an individual born when the food is increasing will have a greater fecundity compared to an individual of the same species born when the resource is at its maximum. To provide a more concrete example of the differences between constant and seasonal environments, I will now focus on two related species of warblers. The fantail gerygone lives in the tropical forest of Vanuatu and New Caledonia, while the grey warble inhabits temperate forests in New Zealand. Field data from both the species shows that they reach equal adult biomass, which is around 5 grams, but the grey warble has a clutch size 2.5 times greater than the fantail gerygone. If we assume that a tropical habitat equals a constant food availability and that the temperate habitat has a seasonal food availability, then simulations using the standard DEB model agree with the expected differences. Both species have nearly equal biomass, but the reproductive output of the grey warble is more than twice that of the fantail gerygone. To conclude, I have shown that resource availability is sufficient to explain intraspecific and interspecific trait flexibility in both constant and seasonal environments, because it drives the individual energy budget. Moreover, the period and amplitude of the resource availability can increase biomass and fecundity, thus providing a mechanism to support the resource and the ENPP rules. However, the reproductive output depends on allocation to soma, so these results may be different for species which are outside of the parameter space that I evaluated. In this way, resource availability is sufficient to explain trait flexibility within and among related species, and seasonality can increase biomass and fecundity, thus supporting the resource and the ENPP hypothesis as explanation to Bergman and Lack's rule. The results that I have shown are based on very strict assumptions and simplifications. Nevertheless, they are a first step contributing to understanding the origin of trait variation, which is increasingly important to forecast biodiversity dynamics under environmental change. Finally, this work was done in collaboration with Charlotte Recapet, Amy Hurford, Suzanne Dufour, and I was funded by Memorial University and by a Global Link Research Award. Thank you for listening, and I am happy to take any questions.